Hey there. Let's talk about the word work. You probably think you know what it means, right? But what if I told you that in physics, a whole lot of what we call hard work, like studying for a huge exam or just standing there holding a super heavy box, actually counts as zero work? Seriously. Let's dig into why this scientific definition is so different.
Okay, so look at this. On one side, you've got all the stuff we'd call hard work in everyday life. Studying, holding something heavy, pushing a rock that just won't budge. But to a physicist, nope, none of that is work. Then, on the other side, you see what does count in science. Pushing a trolley, lifting a book, a bullock pulling a cart. It seems kind of strange, right? So what is the secret ingredient that makes one work and the other not?
And this quote just hits the nail on the head. You can be absolutely exhausted, drenched in sweat, feeling like you've moved mountains, but according to physics, you might have done very little work. It's because science plays by a different set of rules, a much, much stricter set of rules.
All right, so here's what we're going to cover. First, we'll tackle these two different meanings of work. Then we'll get into the actual physics of it and, importantly, how to calculate it. After that, we'll explore positive, negative, and even zero work. And finally, we'll look at the work you do against gravity. Let's get started.
Okay, let's go back to that idea of pushing against the wall. Just picture it. You're giving it everything you've got. Your muscles are burning, you're sweating. I mean, your body is using a ton of energy just to keep pushing, right? But, and this is the key, the wall isn't going anywhere. Because the wall hasn't moved, in the world of physics, you've done absolutely zero work on the wall. It's a tough pill to swallow, but effort and work are just not the same thing here.
So if it's not about how tired you feel, what is it about? What are the magic ingredients? Turns out, for work to actually happen in a scientific sense, two, and only two, conditions have to be met. These aren't suggestions, they're non-negotiable laws of physics.
And here they are, plain and simple. First, a force has to be applied to an object. You know, a push or a pull. Easy enough. But second, and this is the one that trips everyone up, that force has to actually make the object move. There has to be displacement. If either one of these is missing, no work is done. No force, no work. No movement, no work. You absolutely need both.
Okay, so we get the concept now. Force plus movement equals work. But this is physics, right? We love to measure things. We want to put a number to it. So how do we turn this idea into an actual formula we can use?
Yeah, exactly. You push a box across your room. How much work did you really do? Was it 10? Was it 100? We need a way to calculate that. We need to quantify it.
Let's start with the simplest case possible. You've got some object, and you apply a steady force to it. We'll call that force F. And because of that force, the object moves a certain distance. We'll call that S for displacement. That's it, a force and a distance. This is all we need to build our first formula.
And here you have it. Work, which we'll call W, equals the force, F, multiplied by the displacement, S. W equals F times S. It's so elegant, so simple. Makes sense, right? The harder you push, or the farther you push it, the more work you've done.
Now, to be proper physicists, we have to get the units right. So let's take this slowly. W for work is measured in a unit called the joule, and its symbol is a capital J. F for force is measured in newtons with a capital N, and S for displacement is measured in meters with a lowercase m. So putting it all together, 1 joule of work is exactly what you get when you apply 1 newton of force over a distance of 1 meter. A joule is a newton meter.
But, you know, life isn't always that neat and tidy. We don't always push things perfectly straight ahead. Think about pulling a suitcase with a handle, or a kid pulling a toy wagon. You're pulling up
and forward at the same time, right? So what happens then?
This picture shows exactly what I'm talking about. The force is going along the string at an angle, but the toy car is only moving forward horizontally. So not all of your effort is going into making the car move forward. Part of your pull is just lifting it up a tiny bit. Only the forward part of your pull, the component in the direction of motion, is actually doing the work.
And that leads us to a slightly more advanced formula. Don't worry, it's not scary. Work equals F times the cosine of theta, all multiplied by S. Now that F cosine theta bit, that's just the fancy physics way of isolating the part of the force that's actually pointing in the direction the object is moving. It's how we find the useful part of the force, the part that's really doing the work.
So we've got our formulas down, but things get even more interesting. Did you know that work isn't always, well, positive? It can be positive, sure, but it can also be negative. And like we talked about, it can be zero. It all just depends on which way the force is pointing compared to which way the object is moving. Let's break that down. Positive work is the one we all get intuitively. You push a card, it moves forward. The force and the motion are in the same direction. Simple. This kind of work usually adds energy to the system, maybe makes it speed up. But then you've got negative work. This is when the force is fighting the motion. The perfect example is friction. Imagine a hockey puck sliding across the ice. It's moving forward, but friction is pulling it backward, trying to stop it. That friction force is doing negative work, taking energy away from the puck and slowing it down.
All right, let's try a bit of a brain teaser. We already know that if nothing moves, there's zero work. But is it possible for an object to be moving, have a force acting on it the whole time, and still have zero work done by that force? It sounds impossible, but the answer is a definite yes.
So how can this happen? Well, there are two ways. The first one we've already mastered. No displacement. If S is zero, work is zero. That's our wall pusher. But the second one is really cool. It happens when the force is perfectly perpendicular at a 90-degree angle to the direction of motion. If you think back to our formula, W equals F cos theta times S, the cosine of 90 degrees is 0, so it doesn't matter how big the force is, the whole thing just goes to 0. And this isn't just a math trick, it happens all the time. Think about carrying a suitcase through an airport. You're pulling up on the handle to fight gravity, but you're walking forward. The force is up, the motion is forward, that's a 90-degree angle. So the lifting force you're applying is doing zero work. An even bigger example, a satellite orbiting the Earth. Gravity is constantly pulling it straight down towards the planet, but the satellite is always moving forward, perpendicular to that pull. So gravity does zero work to keep it in orbit.
Okay, let's zoom in on that idea of lifting things. Because anytime you pick something up, a pen, a book, a dumbbell, you are actively fighting against gravity's constant pull. And because this is such a common scenario, physics has a handy little formula just for calculating the work done against gravity. Here it is, work equals m times g times h. M is the object's mass, g is the acceleration due to gravity, and h is the vertical height you lifted. Now, if you've done a little physics before, you might recognize that m times g is actually the formula for an object's weight. So you can think of this formula as just work equals the object's weight times the height you lifted.
And of course, let's lock in the units for this one. Work, W, is still in our friend the joule. Mass, m, has to be in kilograms or kg. G, the acceleration due to gravity, is a constant on Earth, about 9.8 meters per second squared. And finally, h, the height, needs to be in meters, m. Getting those units right is absolutely key. Okay, let's pull all of this together into a handy toolkit. Think of it as your cheat sheet for work. If the force and motion are in a straight line, you use the basic formula W is equal to F times S. If the force is at an angle, you just add that cosine term. W equals F cos theta times S. And if you're just lifting something up against gravity, it's W equals M times G times H. 3 common situations, 3 simple formulas to solve them.
So I'll leave you with one final idea to chew on. The sun's gravity is immense, right? It's constantly pulling on the Earth, holding our entire planet in its orbit. And it's been doing this for billions of years. But now that you know the rules of physics, can you explain why, over all that time, the sun has done absolutely zero work on the Earth? It's a huge concept, but the answer is surprisingly simple, and has everything to do with that 90-degree angle we talked about. Pretty amazing to think about. Thanks for tuning in.